remarked to me, some very elderly gentlemen, that there are so many girls in the audience today in a physics lecture. Welcome all of you. And I'd like to now request Professor Ramakrishnan, the Dean of the Natural Sciences Faculty, to say a few words.
Good evening, ladies, gentlemen, and my dear students. On behalf of Tata Institute of Fundamental Research, I welcome all of you to today's public lecture, Black Holes and the Structure of Spacetime, by Professor Juan Maldacena from Institute for Advanced Study in Princeton. Somehow the Princeton is missing here, so I thought I will add that. And this, I believe, Professor Juan Maldacena is one of the participants of the monsoon workshop on string theory, which is sponsored by the International Center for Theoretical Sciences, which is known as ICTS. ICTS is a new center under TIFR, and it has been functioning since April 2007. Committee, and we are very glad about that. And with this, just like all of you, I'm also looking forward to this public lecture. Thank you.
On behalf of the International Center for Theoretical Sciences of the TIFR, I'd like to extend my own welcome to you all this evening. This is the first ICTS public lecture, and we are very glad that the first lecture is by someone who is so distinguished and whose contributions are the centerpiece of most of the research in string theory in the last decade or so. Juan Maldacena is visiting India to attend the monsoon workshop in string theory, which is a program of the ICTS organized by two of India's brightest young theorists. They are sitting right there, Rajesh Gopakumar at the very end and Shiraz Meanwala besides him. And they both actually overlapped with him as graduate students in Princeton. Before I hand over the podium to Shiraz to introduce Juan, I'd like to say a few words about the ICTS, which is a new initiative of the Tata Institute of Fundamental Research, strongly supported by all its faculties and its council. The ICTS aims to bring together different branches of theoretical and mathematical sciences to foster collaborative and interactive research. Its idea originated from successful such centers elsewhere in the world, like the Cowley Institute for Theoretical Physics in Santa Barbara, and the Newton Institute in Cambridge, and the ICTP in Trieste. Here, of course, we have adapted it to our own situation in India. There's emphasis, the ICTS would like to emphasize, there's emphasis on well-established areas as well as interdisciplinary research. And the string workshop is an example of intensive activity in a given discipline actually. And for example, in the last week, we are hoping to organize a session on connection with condensed matter physics and string theory. It's in the spirit of the center, actually. So since September 2007, we have organized approximately 10 programs in a variety of subjects. In condensed matter physics, in particle physics and string theory, biomedical modeling, quantum computation, vector bundles, arithmetic geometry, supernovae and gamma ray bursts, etc. Since the ICTS presently does not have a campus of its own, since it just began last year, most of these programs are being organized at various institutes in India, where the organizers can find the infrastructure to do so. For example, 2 weeks from now, there's a 6 weeks long program in Ayuka in Pune on the cosmic microwave background related topics. And there will be another public lecture actually associated with that here in Mumbai by Professor Lyman Page on the 7th of August, and hope to see you all at that time also. I'll just end by saying that in a couple of years, it's quite unfortunate that this center cannot actually stay here because of the lack of real estate, thanks to the difficulty of finding space in the city of Bombay. And it will move to another rather active location in Bangalore actually. So with these few words, I'd like to invite Professor Shiraz Meenwala to introduce Juan Maldacena.
Okay, so I'm going to introduce our speaker for today, Juan Maldacena, to the audience. Juan is an Argentinian physicist. He was born in Argentina in 1968, so he's less than 40 years old. After his early education in Argentina, he moved to Princeton as a PhD student in 1992, and was in Princeton between 1992 and 1996, where he did a PhD under Professor Curtis Callan. His PhD was on the subject of the entropy, dealt among other things on the subject of the entropy of black holes, something he will probably touch on in his talk today. After his PhD, he moved to Rutgers as a postdoctoral fellow, and then to Harvard as a professor. And in 2001, he moved to the Institute of Advanced Studies in Princeton as a professor there, and has been at the Institute of Advanced Studies since then. The Institute of Advanced Studies, by the way, is where Einstein spent much of the later part of his life. Juan is an extremely distinguished physicist. He's won many awards. Okay, so there's the Sloan Fellowship, the Packard Fellowship, the MacArthur Genius Fellowship, the UNESCO CERN Prize for Young Scientists, the Sackler Prize in Physics, the Xanthopoulos Prize in General Relativity, the Pius XI Medal, the APS Edward Moshe Award, a distinguished lectureship at Stanford University, and the Heinemann Prize for Mathematical Physics. These are the ones he's chosen to list. I'm sure there are many others that would find their way high on our CVs that he ignores because they're inconsequential. Okay. Juan's contributions to string theory have been enormous, have been varied and wide-ranging, but there's one contribution that really stands out. And this was his discovery of the duality, or the identity, the equivalence of a particular theory of gravity and a particular gauge theory. This duality he will surely explain to us in more detail in his talk, so I won't say much more about it. But I just wanted to say that this discovery of Juan's at the end of 1997, apart from being a great discovery in itself, has, in my opinion, changed the discipline of string theory. Okay, string theory, which has always been fertile and fantastically, intricate and beautiful mathematical structure pertaining to quantum gravity, has, since Juan's discovery of this duality between gauge theory and gravity, found itself connecting more and more to other areas of human knowledge, especially in physics, but other areas of physics, like the traditional study of the strong forces inside protons, or condensed matter physics, and perhaps promises to expand its frontiers wider into the realms of knowledge of physics. So apart from being a significant, a fantastic contribution in its own right, in my opinion, it's changed an entire discipline. Okay? Juan has done, apart from his discovery of the ADS-CFT correspondence between gauge theory and gravity, Juan has done many, many other very significant things. But I won't try to tell you about that. As I mentioned at some point, Juan's PhD work was on black hole physics, and black holes have always been close to his heart. He was thinking about black holes that led to the discovery of this magnificent ADS-CFT correspondence. And in his lecture today, Juan will tell us more about the mysteries of black holes and how the attempts to understand them have or promise to change our perception of the universe. Okay, so with that, I'll quit. Thank you.
Now we'd like to present a token of our appreciation to Juan and a memento. So may I invite Rajesh Gopakumar to give this memento to Juan.
I'm very happy to be here in Mumbai, here in India, after so many years of Rajesh and Shiraz telling me so much about this wonderful place. And of course I knew the Data Institute for all the wonderful physics that came out of it, and all the wonderful people who are here doing very interesting research, especially in this area this area that I know of string theory. So I will be talking about black holes and the structure of space-time, and I would like to tell you a kind of history. I mean, the history of black holes and how we started understanding some aspects of black holes, and then one thought one understood black holes, but then there was a surprise, and there was surprise after surprise. So I'll first give you an outline of what I'll talk about. So black holes were some solutions of Einstein's equations that were found by Carl Schwarzschild. And after he published his solutions, then some people thought it was wrong, or they were not very physically relevant. For example, Einstein thought, oh, there must be something wrong with these solutions, they look wrong. But then eventually it was understood that they were actually unavoidable, and that very massive stars would actually form black holes. So they were very generic and really physical objects. And then Hawking realized that black holes are actually not black, they can be white or red. And he further said that black holes were incompatible with quantum mechanics, that black holes imply that quantum mechanics must be wrong and must be replaced by something else. That's what he thought. But then came string theory, and string theory showed that gravity is compatible with quantum mechanics, and not only that, but it said that gravity in certain circumstances is related to particle physics, and there is some picture of what space-time is, at least in those circumstances. So, but before I get into black holes, which are objects that arise in space-time geometry, I'd like to remind you or explain some concepts some previous concepts we need to understand in order to appreciate what we are talking about. So the first concept is the concept of special relativity, which says that two observers that are traveling with constant velocity observe the same laws of physics. I mean, this was something that and we would not notice it, even though we are traveling at around 1,000 kilometers an hour, we are not noticing that fact. So the idea is that two observers, so the two observers here will both, if they do measurements inside their little rooms or airplanes or wherever they are, they will not notice that they are moving relative to each other. Now, special relativity becomes more surprising once you put it in together with another law of physics, which is the idea that there is a maximum propagation for the maximum propagation velocity for signals, which is the speed of light. So the idea is that this maximum speed is actually a law of physics, which has to be the same for all observers. And once you realize that, so if you have two observers, one moving, one here and the other moving, if you use your everyday intuition, you will think that this observer will see light moving faster than this observer. Right? So that's the everyday intuition. And the surprise is that both observers see actually this object, the light, going at the same velocity. And the way that works is that distances that the second observer sees are smaller. So for the same proper distance here, this observer would see a shorter distance. And the time would go slower for this observer. So the two observers perceive distances and times in different ways. That's how this observer can manage to see the same velocity of light as the observer who is at rest. So this is certainly not intuitive. It's something that was found experimentally, and it is the way nature works. So this one other way to explain this, one other surprise is that if we time depends on how you're moving, and so if you have two identical twins, and one moves and travels at fast velocity and then comes back, and the other one stays at rest, then the one who moves faster will be younger. And this is the way it works. This is experimentally tested for elementary particles, and indeed they behave this way. The two twins are not completely identical because this suffers some acceleration, well, this one didn't. So that's the one that gets younger, comes back younger. Now, the lesson that special relativity tells us is that the space and time form a single entity, which is space-time. How we separate into space and time depends on how we are moving. So two observers moving relative to each other will perceive space and time differently. In the same way that what is left for you and right for you is different than what is left and right for me. So depending on how we are standing, we perceive left and right differently, or forwards and backwards differently. In the same way, space and time is perceived differently depending on how we are moving. So that's the first point I want to make through the first three slides. Now, for a second, let's move on to some other apparently different subject, which is the force of gravity. Now, in our everyday experience, we see that heavier objects fall faster. That was encapsulated by Aristotle. Heavier objects will fall faster. But actually, once you remove the effects of the resistance of the air, you find that actually all the objects fall in exactly the same way. So if you had a feather and a rock, both will fall exactly in the same way if we remove the air. So and that, in fact, becomes sort of a law of physics. So that fact, which is based on experiment, becomes a new law of physics, which says that essentially everything falls in the same way in a gravitational field. So it's a very fundamental fact about the force of gravity. And it doesn't happen for other forces. So for example, if you have a magnet, the magnet will attract a piece of iron, but it will not attract a piece of wood, for example. So magnetism affects substances in different ways. But gravity affects substances in different ways, but gravity affects bodies in precisely the same way. It makes them move in precisely the same way. under the influence of the gravitational field of the Earth, but both will move exactly in the same way and they will feel as if they are floating. I mean, you can also take these zero-G rides in an airplane and you would feel that you are floating the same way that Stephen Hawking would feel he's floating. So this concept of space-time and gravity come together in the idea of general relativity. So general relativity is a theory of gravity, and what it says is that gravity is due to the geometry of space-time. So space-time is not sort of a flat space, but it can be curved. And the idea is that heavy objects curve the space and time around it, and then if you have a second very light particle moving in that space-time, it will follow the sort of trajectory of minimum length, or more precisely, the trajectory that maximizes its time. So in some sense, the particle wants to live as much as it can, and that's the trajectory it chooses. And the fact that all objects move in the same way is due to the fact that all the particles are feeling the same space-time geometry. So everybody is seeing the same universal geometry. Now, it's important that the geometry of space-time includes both space and time. So, and in fact, in the same way that the perception of time depends on how we are moving, the perception of time depends, or how time flows, depends on your position in a gravitational field, for example. So if we are here on the gravitational field of the Earth, and we are on the lower floor of a building, and we have another person in the upper floor of the building, and then they have two clocks, and they decide to compare these clocks, they would find that the clock in the bottom of the building goes more slowly than the clock on the top of the building. So the flow of time is affected by the gravitational field. Now, of course, you've never seen this because you've never had precise enough clocks. But if you do this experiment very carefully with a precise enough clock, you would see that there is a very tiny difference in how time flows in a gravitational field. Of course, if the gravitational field were stronger, then this effect would be stronger. But when we talk about the geometry of space-time, so we're talking both of space and also of time. So again, the twin paradox in this case would be that if we go very close to a very massive object, and then we come back out, due to the fact that this person was in a stronger gravitational field, will come out younger. Now, Karl Schwarzschild found the geometry, the space-time geometry, outside a spherical massive body. So he thought, well, suppose you have a star of a certain mass. He solved Einstein's equations that determine the space-time geometry, and among other things, the space-time geometry tells us how time flows. So if we have a clock here far away, it will tick with some rate, let's say, and then as we get closer to the star, the clock ticks more slowly. So this clock goes a little more slowly than this one. And so one of the characteristics of the space-time geometry is precisely how fast these various clocks will tick. And so as if we take a star of a given mass and we make it smaller, then we're exploring more of this geometry, and then this clock will start going more slowly, okay, as the effects of gravity becomes a bit stronger. And then if we make it smaller than the critical size, you find that at some point time stops to flow. So that clock seems to have stopped completely. And this is what Einstein didn't like. So Einstein didn't like the fact that there would be a point in space-time where time doesn't flow. He thought this must surely be unphysical, and this must not be a good solution, and there must be some reason why this solution is not allowed and should be thrown out. Now, it was later understood that actually the geometry continues behind that surface where time apparently stops, and that surface is called the horizon, and it continues into some region in the interior, and it ends on something called the singularity, which is a region where the space-time curvature becomes very, very strong. So what happens is the following. So if you were falling into this black hole, you don't feel anything special when you cross the horizon. Time for you will continue to flow. It's just time for an outside observer that doesn't flow, but time for you flows. and then that would rip you apart and you would probably die. Okay, so it's not very good to go to the singularity. But something important is that you don't feel anything at the horizon. So that surface that looked very bad to Einstein actually is a very fine surface. Locally, you don't feel anything special at that surface. Now, to explain how this could be, that some surface is very special from one point of view, but not from some other point of view, there is this analogy that people have proposed. So imagine space-time as a river, and somehow the flow of time is analogous to the flow of the river. And so imagine a river which has a waterfall, and then the velocity of the water starts getting faster as it goes to the waterfall. So here the velocity of the water is something, and then it becomes a bit bigger here. Now imagine that in this river you have some fish that are swimming on the river, and the fish can swim at some maximum velocity, which we will call c. So c is the maximum velocity at which the fish can swim. Now suppose you have some fish that is over here, and start swimming up current, then since it can fish faster than since it can swim faster than the velocity of the water, it can just go out and get upstream as much as he wants. Now there is a point here where the velocity of the water is precisely equal to the maximum velocity at which the fish can swim, and if the fish starts swimming upstream, it will just remain there. So this is a very special surface because the fish is just stuck there, it's swimming, but it's not really moving anywhere. And finally, if we have a fish, if the fish is in this region where the velocity of the water is faster, it will unavoidably fall into the waterfall. That's analogous to the singularity. No matter how fast the fish swims, it will fall into the singularity. Now, when the fish is swimming around in the river, the fish doesn't feel anything special about this point. All the fish sees is the water. Let's say it's a muddy river. He cannot see the banks of the river or anything. He's just swimming there and doesn't feel anything special here. I mean, here when he falls into the waterfall, he does feel very bad. When over here, he doesn't feel anything special. And he doesn't notice that he moved into the region where he will fall into the waterfall. Okay, so we've seen several aspects of black holes, and these aspects were slowly understood. And by the 70s, it was understood that all these features were understood. There is a horizon. You can fall behind the horizon. If you fall behind, you cannot come out. Secondly, a very massive star can collapse into a black hole. And also that there are objects in the sky that also seem to be black holes. So let me just mention a couple of words about real black holes. So black holes can be produced when you have a very massive star, so a few times more massive than the sun, and then those stars, after the nuclear reactions go on and they become a bit smaller, they could collapse and become black holes. So that's one class of black holes that there is some evidence for. And then there are some other black holes which are much more massive, which sit at the center of galaxies. And those are very big. They have the size of the solar system. Now let me say a few words on how we see or what evidence we have for these black holes. Now in principle it would be hard to see a black hole because it's black, it doesn't emit anything, so it's not like a star that you can see. However, in principle, if a black hole moves in front of some star, it would bend the light of those stars, and in principle you could see them this way. I mean, that they've been looked for in this way, but none have been seen using this technique. Now, in some fortunate cases, the black hole is surrounded by some gas, and when the gas falls into the black hole, it heats up and it emits some radiation, and then people see that radiation. And then they compare so you don't see the black hole directly, but you see the radiation coming from matter falling into the black hole. So there is one particular star that emits visible light, and at the same time there is an X-ray source. And what's believed to happen is that you have a big star, and there was a companion star that collapsed into a black hole, and then there is matter falling into this star, and then you see radiation coming out of there. And you don't see the black hole directly, but you see some indirect evidence. And for black holes in the center of the galaxy, it's a similar story. Now we go to much longer distance scales. This is 90,000 light years, so this is very big. Here is a galaxy. This is the whole galaxy. And then there are some jets of particles that come out of the center. So there's something very energetic at the center that is emitting all these particles. And when you look at the center with a high-resolution telescope, you see a very big disk of 400 light years, so it's still very big, much smaller than the size of the galaxy, but very, very big compared to ordinary astronomical, well, distances, let's say, solar system size. So this is the disk that is falling into this black hole. And then you compare the properties of this disk with what you would expect for a black hole, and you find that they more or less agree. So that's, but of course the black hole in this case would be much, much smaller than what we can see on this picture. So the black hole is there, a little tiny dot at the center. And many galaxies similar to ours have a black hole at the center, and including our galaxy, there's some evidence that there's a black hole at the center of our galaxy. Now let me make a side remark here and ask the question of whether we should be scared about all these black holes going around the universe. Now black holes are bad if you fall in. So if you fall in, you really shouldn't do that. So, but if the gravitational force outside the black hole is exactly the same as the gravitational force outside the star. So if we were to replace the sun by a black hole, the Earth would continue to go around the black hole and would not feel anything special. Of course, we wouldn't see the sun, and there would be global cooling, so global warming. But in terms of the trajectory of the Earth, it would be exactly the same. Now, the nearest black hole is very far away, so there's nothing to worry about. And if you're worried about the gravity, you should be worried about falling from a ladder more than falling from a black hole. But one thing we learned is that black holes are very good for theoretical studies. So you can, it's very good for investigating them theoretically. And I'll try to explain actually why this is actually true. So it's not just a joke, but it's true that they're very good for theoretical studies. Now black holes have some surprising properties. So just the black holes predicted by the theory of general relativity have some surprising properties. So one of them is that independently of how you form a black hole, the final black hole will have a shape and properties that are completely universal, independent of how you make it. I mean, it will depend only a few parameters. It will depend on the mass, the angular momentum, and the charge. So you can have stars of a given mass could be very different. So you could have red stars, blue stars, etc., all kinds of different stars. They could have different shapes, and so on, different chemical compositions. However, if these stars were to collapse to black holes, they all collapse to the same type of black hole. The black hole is only specified by the angular momentum, so how fast it is rotating, and the total mass, essentially. So that's one interesting property. So it points out to a very deep simplicity of black holes. Now the second, the second property is related to the following. Suppose that you have some complicated process, like let's say two black holes collide and two black holes collide. Now if two black holes collide, they will emit some radiation, some gravitational radiation. So they will, for example, lose some energy through gravitational radiation. And so the final mass of the final black hole might be smaller than the initial masses of the two black holes. And you might wonder, well, what's the maximum gravitational radiation you could emit? Could all the mass of these black holes go away and become gravitational radiation? Now what was found was there is actually a very simple relationship that needs to be obeyed, which is that the area of the final black hole has to be bigger than the sum of the areas of the two initial black holes. So the equations governing this process are very, very complicated. So only now with very, very fast computers you can actually compute this process and find out what's going on. They're very, very complicated equations, but there is a very simple result, which is that the area of the final black hole has to be bigger than the two initial areas. So this is an interesting property of those equations of general relativity. It's an interesting property of space-time dynamics, of space-time geometry. So far, we've been discussing black holes according to the classical properties of black holes. So we are studying the evolution of space-time according to the classical equations of Einstein. So the Einstein Theory of General Relativity. Now, when we include quantum mechanics, quantum effects, find a new surprise. And that surprise is that there can be white black holes. So Hawking, so let me first summarize what this is, and then I'll try to give an explanation for why it is so. So Hawking found this result, which is that quantum mechanics imply that black holes emit thermal radiation. So what this means is that the black hole is a little bit like a piece of coal. They will have a temperature, and the temperature is such that the temperature is smaller for bigger black holes. So as the black hole gets smaller, the temperature gets higher. So if you have a black hole of some size, it might have a low temperature. It will look more or less black. If it becomes smaller, it can become hotter. It could look red. And if it becomes even smaller, it could become so hot that it will look white. The same way that if you have a piece of coal and you heat it up, it will look red, and then if you heat it up even more, it might look white. Now, in order to give you an estimate of what the temperatures are for various black holes, so let me here quote some values. So for example, for a black hole of the size of the mass of the sun, the temperature would be 10 to the minus 7 Kelvin. So this is a very, very tiny temperature. And it's so tiny that it would be impossible to measure in practice for a black hole of the mass of the sun. As we saw, there are some black holes in the sky which have a mass comparable or a bit bigger than the mass of the sun. And unfortunately, it's not possible to measure those temperatures. Now, if we had a black hole of the mass of the Earth, it would be a bit bigger, but still very small. But if we had a black hole of this mass, which is roughly the mass of a continent, of let's say the Indian continent, subcontinent, we would have a temperature which is equal to the temperature to the wavelength of white light. So this black hole will look white. It will be a very, very tiny speck, but it will look white. Now, let me try to explain why thermal radiation is emitted from black holes. So, So here we need to use the laws of quantum mechanics, and in particular the laws of relativistic quantum mechanics. And in those theories, we can have particles that can be created and destroyed. So if you have enough energy, the famous relation of E equal to mc squared allows you to convert energy to mass and to particles and so on. And this can happen if you have enough energy. Now, according to this theory, even the vacuum, when you don't have any particles, it's somehow a complicated thing where particles can be continuously created and destroyed. So the idea is that you can have a pair of particles, one with positive energy and one with negative energy, that come out of the vacuum and then join back together. Now, in flat space, you are not allowed to have particles of negative energy, so all energies have to be positive. And so you cannot, this particle with negative energy cannot go away and become a real particle. So it can only exist for a very short time, so that the uncertainty principle forbids us from measuring its energy, so that we cannot really complain that this law of positivity of the energy is really violated. Now, this is what happens in flat space. In the presence of a horizon, you also have this process of the creation of a particle with positive energy and one with negative energy. But what happens is that the notion of positive energy for the observer outside and the observer inside are actually different. So these particles have negative energy from the point of view of the outside, but from the point of view of the inside, they are perfectly fine particles, and so they can fall into the horizon, into the singularity and disappear, and then this particle can go to infinity. So that's the basic idea of why this can happen, and you can calculate it more precisely according to the known rules of particle theory, quantum particle theory, and you get the result that Hawking obtained. So this implies that when we have a black hole, black hole will have a certain life, so the black hole is formed, it will start emitting this thermal radiation. As it emits radiation, it will lose mass, and so it will have a finite lifetime. So you calculate how fast it loses mass, and then you can see that it will have a finite lifetime. So let me just quote the lifetimes for various black holes. So if you have a black hole of the mass of the sun or the Earth, it will live much longer than the age of the universe. So for the black holes that are produced through astrophysical processes, we saw the temperature was very small, and this effect is also very small, so we will not see them decaying completely. Now, a black hole with an ordinary mass, so a mass of an ordinary object, let's say 100 kilograms, would evaporate in less than a millisecond. And in doing so, it will convert all its, the rest mass, so this 100 kilograms, it will turn completely into energy, so it will be an explosion much worse than a nuclear bomb. So don't be very near a small black hole. Small black holes are dangerous. Now, a black hole of the mass of the order of a mountain, which is this mass over here, produced at the beginning of the Big Bang, would be evaporating now. So if you are really hoping to be able to see evaporating black holes, you somehow might want to hope that perhaps at the beginning of the Big Bang you produce this kind of black holes, and then maybe you see them evaporating now. None of these have been seen, and in fact probably none of these black holes were produced at the beginning of the Big Bang, according to the standard theory none will be produced. So we're out of luck, and we can really, it seems pretty hard to measure Hawking radiation. Now there are some scenarios or some theories where very small black holes will be produced in particular accelerators. I don't think they are particularly likely scenarios or likely theories, but they could in principle be produced, but they would decay very quickly. However, so this problem of black hole evaporation, even though it's hard to measure experimentally, and perhaps sometime in the future will be measured experimentally, it really gives rise to several interesting theoretical problems. And a lot of the research, well, there is a branch of black hole physics which has dealt with understanding these theoretical problems. And the theoretical problems arise because black holes are mixing quantum mechanics and gravity, and these theories are hard to mix. So I'll explain a couple of these problems. So first I'm going to explain the first problem, which is to understand a little better why black holes are hot. So why black holes emit this thermal radiation, what does that mean? And the second is the problem of information loss. So I'll describe these two problems in turn. First I'll describe the first problem. Now, temperature, of course, is an everyday concept, and in physics we explain temperature as the motion, as due to the motion of microscopic constituents. So if you have a gas, you have a cold gas versus a hot gas, so the particles are exactly the same, but in the cold gas they are moving more slowly than in the hot gas. So the temperature is somehow due to the motion and the energy that you have in these microscopic constituents. The faster they are moving, the hotter it is. Now, and anything that has some temperature, we explain the temperature in this way. So this is the so-called microscopic explanation of thermodynamics, or microscopic explanation of temperature. So heat, in some way, heat or temperature is due to the microscopic motion of the constituents of matter. And for any system we encounter in the lab, we like to find these constituents. And for ordinary systems, these constituents are the atoms or fundamental particles that make up ordinary matter. Now there's a closely related concept, which is the concept of disorder. It's technically called entropy, and it's essentially the number of configurations of these constituents. And there's some law, which is the first law of thermodynamics, that gives us this disorder if we know the entropy and the energy. And for the case of the black holes, this entropy, this disorder is proportional to the area divided by some very small distance scales, which is related to G Newton. So it's the area in units of 10 to the minus 33 centimeters. So this is a very tiny number. That means that this quotient, if this area is a macroscopic distance, this entropy is a very, very big number. So it's much bigger than the disorder that is present for any ordinary system. So for a glass of water, you can calculate again this quantity in terms of the number of configurations of the molecules of water, and you find some number, and the number you find is much, much smaller than the number you would find for a black hole of the size of that glass of water. So this number is very big. And there is a law from thermodynamics which says that the disorder always increases. This is perhaps one of the most intuitive laws of physics, which says the disorder increases, present in everyday life. For black holes, this second law of thermodynamics comes just simply from the classical equations of general relativity. So the classical equations imply that the area of the black hole is free. So what's a thermodynamic property has become the property of the classical equation in gravity. So the questions are, what are really the microscopic constituents of a black hole? So we explain always temperature in terms of something moving. What is moving in a black hole? The black hole seems to be just a single classical solution, a single space-time configuration. What is really moving there that is giving rise to this temperature? And this, if we understood this, we will understand something about the nature of structural space-time, because a black hole is really a property of space-time. It's a hole in space-time. And if we understand what gives rise to temperature, we'll understand the microscopic, let's say, atoms of space-time. So what are the microscopic things that actually make space-time? So that's the first problem. So that's a problem that's been with us since the 70s. And the second problem is the problem of information loss. So we can form a black hole in many different ways. So let's say we throw a book into a black hole. But the black hole, independently of the book you throw in, the idea of Hawking would be that it evaporates always in the same way. It always emits thermal radiation that carries no information about what fell into the black hole. But according to the rules of quantum mechanics, if you form something in two different ways, the outcome should be different. So if you form something in one way, the outcome should be something. If you form something in a different way, the outcome should be something different. So the information about what you put in should be preserved under the evolution. Now, there are many situations in which information is apparently lost. For example, if you take the book and you burn the book, it seems that you lost the information about what was in the book. But you would, in principle, be able to recover that information if you collected all the radiation coming from the book and you were infinitely powerful and so on. You would, in principle, be able to do that. Of course, in practice, you would not want to do that, but at least we know the equations that govern this process. We know that if you solve the so-called Schrödinger equation, the equation that governs this process in quantum mechanics, you would be able, in principle, at least to recover that information. So the question is, what is the equivalent equation for the case of black holes? Is there such an equation, or is there not such an equation? If there isn't such an equation, it means that the laws of quantum mechanics have to be different. We have to modify the laws of quantum mechanics. And the bad news is that we don't know how to modify them. That there are many different modifications, and we would be a little lost. So in order to really answer this question, we need to have a theory that puts together quantum mechanics and gravity. And that theory is, string theory is a theory that does that. It puts together quantum mechanics and gravity and allows us to analyze these problems. So string theory has a very long history, and there were many people working on string theory. And it was born in the around 68, and it was reinterpreted in the 70s. There was a lot of activity in the 80s, and then in the 90s there were several connections found among different string theories. So one of the ideas of string theory is that you replace particles by strings, so little tiny particles is replaced by a loop of string, and that's essentially where the name string theory comes from. But this fact is not what's really most important. What's really important is some mathematical theory, let's say, that is such that when you consider interactions, it leads to, including quantum effects, it leads to a finite and consistent theory. So it's a theory that gives you reasonable answers. So what's important here for our purposes is that it is some theory that unifies gravity with quantum mechanics. Now, in addition, it will unify all the other interactions, and I won't discuss about that aspect of string theory, which is a very interesting aspect, but for our purposes here, all that is important is that we can describe gravity and quantum mechanics in a single framework that makes sense. Now, the problem of black holes in string theory was analyzed, and first very simple black holes were studied, and those black holes, those string theories will have some parameter that you can change, and you can turn the black hole into a collection of strings and some other objects that appear in string theory called D-branes. And so these are some objects whose rules we know, and we can count how many objects we can make, and so in some sense we can count the disorder that you have in these objects, and you can arrange these objects in many different ways. And there are some precise mathematical rules that tells us how you can arrange them. And when you count how many ways you have of arranging them, it's equal to the ways in which you have, it's equal to the entropy of the black hole. Now, that was very nice, but the black holes you could describe that way were black holes that have zero temperature and for which you couldn't discuss this problem of the information paradox. So in order to analyze those other black holes, it's interesting to study a particular relationship between string theory and particle theory. So it turns out that there are certain spacetimes, these are spacetimes that are negatively curved. So this picture here is a picture of two-dimensional space that is negatively curved. Was drawn by Escher, painted. And so here all these fish all have the same proper size, they all have the same size. And the fact that there is an infinite number of them when we go to the boundary here means that the boundary is really infinitely far away. It also has negative curvature. And well, this is a simple two-dimensional situation, but we can add time to this story and have a negatively curved space-time. Such spacetimes have a kind of boundary at infinity, so if we were living in such a spacetime, we'll see our ordinary four-dimensional spacetime. There would be some boundary, some two-sphere at infinity, and the whole gravitational theory in the interior, everything that happens in the interior is described in terms of a theory of particles at the boundary. So that's the idea. So this is a picture of how this is supposed to work. So you have some particle moving in the interior of the spacetime. So let's say you have a mass that is moving in the spacetime. The spacetime is curved, and the curvature of this kind of negatively curved spacetime does not allow a massive particle to reach all the way to the boundary. So massive particles are bound to move here in the interior, and that's the interior description. And alternatively, you have an alternative description in terms of some particles that move on the boundary. So these are different kind of particles. They are very similar to the particles that we use in particle physics, but they live in a space without gravity. They live on the boundary of the space. So if we were living in our four-dimensional space, these particles will live on a two-sphere at infinity. They are moving, and depending on how they move, they describe different particles in the interior. So the same kinds of particles on the boundary, moving in different ways, describe different particles in the interior. And so gravity in the interior is described by this interacting theory of particles on the boundary. And so in this way, you can also describe black holes. So if you have a black hole in the interior, the black hole in the interior of this spacetime is described by these particles that are moving on the boundary. And here on the boundary, you have lots of particles moving in many different ways. And these are very similar to the atoms of the gas that we saw before. So the temperature of the black hole is related to the temperature of these particles. It's related to the fact that these particles are moving in random ways, and there is a lot of disorder associated to how these particles are moving. Now, in this kind of description, these particles are not only describing just the black hole, but the whole space-time outside the black hole. So these particles are describing the whole interior of the space-time geometry, including the black hole. And the nice thing about this is that this theory on the boundary obeys the standard rules of quantum mechanics. So it has an equation similar to the equation I mentioned before that governs the evolution in quantum mechanics. So therefore, the black hole in the interior also follows the same rules. So this is some argument that shows that the black holes are consistent with quantum mechanics, and in string theory, we use this description for describing black holes, and it is consistent with quantum mechanics. And this is definitely a prediction of string theory, that black holes should be consistent with quantum mechanics, and it's a really testable, well, it is in principle testable, but it's hard to test. I mean, it's very difficult to make a tiny black hole and really see whether it obeys the rules of quantum mechanics. But it's really a definite prediction of string theory that it could have been otherwise. I mean, Hawking had suggested that black holes actually destroy information, that you couldn't make it consistent. So this is definitely a prediction of string theory. Unfortunately, like all the predictions of string theory known today, they are very hard to test. and we still have to come up with a prediction of string theory that we can actually test in the near future. So in conclusion, I would like to give you the message that these black holes are fascinating objects where the geometry of space-time is deformed in a very dramatic way. There are many different aspects of black holes, so you can concentrate on studying the black holes that are in the sky, that you can see with the telescopes, or you can see directly with the telescopes. And for those black holes, the laws of classical physics are enough to describe them. But if you imagine for a second that you have smaller black holes with quantum mechanics give rise to very interesting theoretical challenges that sort of put to test our theories. So if you have a theory of quantum gravity, you can try to understand how your theory describes black holes. And it has to do that in certain consistent ways. And thinking about this problem has led to the development of better theories of quantum gravity. And string theory can describe black holes in a consistent way. And in this description that we saw, the space-time in the interior, and also the black holes, is an approximate concept that arises from more elementary particles living at the boundary of space-time. So these particles living at the boundary are in some way like the atoms of space-time, the fundamental constituents of space-time, and they can explain everything that happens in the interior of this space-time. So far we understand how to do that only for particular spacetimes, these spacetimes that have negative curvature. And unfortunately we live in a spacetime with slightly positive curvature, so we can't directly apply what this description for our positively curved spacetime. But hopefully a similar description might work for our positively curved spacetime. Okay, thank you.
Thank you, Juan, very much. It was, as expected, a lecture that bore the stamp of originality that all of us string theorists have known to expect from Juan. So we'll have time for a few questions from the audience. And the questions, please make them short and concise and to the point and relevant to the talk that you heard today. So if you have any questions, please put up your hands and please come into the corridor and speak.
Used in other condensed matter systems, because usually, or other problems in particle physics, because usually the dimension in which the theory lives is the same. So we have the quarks live in 4 dimensions, the nuclei, which are the effective description of the nuclear force, at long distances also live in 4 dimensions. Here we have an effective description in terms of particles that live in 1 more dimension. And so that's a new aspect of this story. Yeah.
Thank you for a very lucid talk. There is one aspect which I did not understand, and I'm not from string theory background or even particle physics. You said that the area of 2 merging black holes, A1 plus A2, is always less than the final black hole that is formed, A.
Yeah, that's right.
Now first, why is it so? And second, why is this so significant?
Right. Well, why it is so, it follows from the equations from Einstein's equations. So you have to use Einstein's equations plus the condition, plus the fact that the energy of matter is positive. Essentially, that's what you need to use. And it's hard to explain in simpler terms. Now, it's significant because when you interpret the area of the entropy, that increase translates into the second law of thermodynamics, which is something that in ordinary systems does not come from just the classical equations. I mean, you have the wave equation. Well, the entropy is 0 in the beginning, and any solution of the wave equation will continue to have 0 entropy. So the entropy comes from some microscopic description and comes from doing statistical physics. Here we solve the classical equation and we find relations that are thermodynamic relations. So that's a surprise. And that doesn't happen for any other system.
string theory we use to visualize physical things like matter changes to photon and photon changes to matter.
Yeah. So, I mean, we really, that process of electrodynamics. So those are rules we certainly understand well, and we have that picture. So string theory is something that is trying to describe what the nature of the photon is and the electron. So where quantum electrodynamics came from. So that's what it's trying to describe. So if the objective is only trying to understand how the photon creates electron and positron, we have quantum electrodynamics. So we're trying to find a more sort of deeper description that also unifies the photon with the electron. So the photon and the electron would be the same string, but oscillating in different ways. So the string oscillating in one way is the photon, the string oscillating in a different way is the electron. And the same process is described by a string coming in and splitting into two strings. Those are the electron and the positron.
Hello. Excuse me, sir.
That's a question.
Sorry,
Yeah, if you can just wait a second.
Oh, fine. I should say.
Okay.
So you said that on boundary there are particles corresponding to each body in the universe. So do we know anything about how the particles on the boundary corresponding to different bodies interact?
Yeah. So it depends on how simple those bodies are. So if they're very simple, like for example, elementary gravitons, then we understand. So the interaction of 2 or 3 elementary gravitons, you understand how to describe it on the boundary. When it starts getting more complicated, we don't understand how to describe it exactly. Because as I said, so one simple particle in the interior becomes a complicated system on the boundary. And so you need to do a complicated calculation, which in principle you could do if you were very powerful, but we are not so powerful in practice. And so it's not for everything that we can do the actual computation. And so learning how to do these computations is actually one of the fields of research, trying to understand how to translate from things in the interior to things in the boundary. And actually, in fact, this relationship is sometimes used in the reverse. So sometimes the simple theory in the interior can be used to calculate these more complicated processes in the boundary. So that's... Yeah.
So I want to say that actually, how can we tell that there is a presence of black hole in space when we move in the space? Is there any way to detect the presence of black hole in the space when we are moving in the space?
If there is a way to see the presence of a black hole in the space, you mean for black holes in our universe?
No.
Oh, for these cases?
No, not like that. But suppose we are moving in a space.
Yeah.
So you told that the black holes means we know much about black holes till date. So can you detect the presence when we move in the where is it actually located?
Is the question, can you detect a black hole when you move in its vicinity?
In space.
If you move in the vicinity of a black hole, how do you...
So if you have a black hole and you move close to it, you will follow a certain trajectory, and then you can compare the trajectory in which you move with the trajectory you expect near a black hole. So, well, the answer is yes.
And one more question, sir. That you told that the particles are merged and deformed to form a string. Particles are change its shape to string theory, means when you come to string theory. So particles are converted to string, and then we study the string theory. So if when the string vibrates, so which kind of energy it will emit?
Well, when the string vibrates, it emits other strings. So in ordinary particle physics, energy is carried by particles. So, for example, a hot gas will emit photons, right? So in string theory, will emit just some little tiny string, which is a string oscillating in a particular way, which describes the photon.
So will that be in the form of particle or in the form of wave?
Well, the string is like any other, a small tiny string also has the particle wave duality. I mean, it's described by a wave, has wave-like aspects and also particle-like aspects.
Thank you.
Yeah.
I am not even a physicist, so thank you for communicating some of the fascination of your field. Which of this did you show in 1997 and how did it change the world?
Well, that was this relationship between the theory on the boundary and the theory in the interior. So this relationship between particle physics on the boundary and particle and the gravity in the interior. And this is something that's been studied a lot and more has been understood than, of course, was understood in 1997. There is a lot of research that enabled us to understand this with more and more precision.
So you said that a black hole will emit radiation and so it will lose mass. And when it loses mass, the Schwarzschild radius should decrease.
Right.
But in the next part of the lecture, we saw that the entropy should increase and the area should increase.
Right. Yeah, so the entropy should increase if you neglect the effects of Hawking radiation. So when you emit radiation, the entropy decreases, but this radiation is thermal and it carries entropy away. So if you sum the entropy of the radiation and the entropy of, and you consider the area, you find that actually the entropy doesn't actually increase. So the Hawking radiation process is actually increasing the entropy. There's more entropy in the radiation than there was in the initial black hole.
Okay, maybe one last.
Good evening. You mentioned about evaporating primordial black holes.
Yeah.
You also said that they haven't quite been detected till
Yeah.
now. How would you hold gamma ray bursts in this aspect?
Well, there are some more conventional theories for what gamma ray bursts are. So they even have been linked to supernovas. So there are some cases where people observe the burst and they observe the supernova. So the more standard theory is that they are supernovas.
Okay, so before we conclude this session, we would like to invite all of you in the audience to tea in the main building in the West Canteen. So please do join Professor Maldacena and all of us for tea. And before we disperse, let's thank Juan again for